Assalamualaikum to Dr Aizuddin Supee and all fellow friends. So we are from group 2, we'll be presenting experiment 1, Marcet Boiler. These are our group members. The first one is Fakhrul Rasyid, and we have Ahmad, Lukman, Aqil, Mohamad Hanis, and myself, Afina Ainna. For the introduction of the Marcet Boiler experiment, this experiment demonstrates the relationship between the pressure and the temperature of the saturated steam. So this is what we call thermodynamic. So this is also essential for designing and operating steam-based systems like boilers, turbines, and heat exchangers in industries such as power generation, chemical processing, and also oil and gas. So how does this experiment works is the first one, the Marcet boiler, the boiler will heated up the water in a sealed vessel, generating steam as the temperature and the pressure rise. Also, we have the thermometer and the pressure gauge monitor that attached to the Marcet boiler that will monitor these changes, the temperature changes, while a safety valve prevents over pressurization. This experiment also validates steam table data, ensuring the safety, efficiency, and reliability of steam systems by providing practical insights into steam behavior under varying conditions. Next up is the applications in real life. So the first one we have the HVAC systems, which is the stands for heating, ventilation, and air conditioning systems. So this system is often use steam as a heating medium, and the knowledge of steam behavior under different pressures is essential for designing efficient and reliable heating systems. Also, the second one, we have steam power plants. So, in power plants, steam is used to drive turbines for electricity generation. So, the Marcet boiler experiment will help us understand the relationship between the pressure and also the temperature of steam, which is critical for optimizing the efficiency of the steam cycles. Okay, the third one in figure 4, we have boiler and pressure vessels. So the principles that we can learn from the Marcet boiler is applied in designing and for the operation of the industrial boilers and also the pressure vessel. So to understand the pressure temperature relationship is to ensure the safety and the efficiency in high pressure system used in industries like chemical processing, food production, and oil refining, where we know the higher the pressure, the higher the temperature resulted in. So all of this concept is applied in this all of these systems. Next is objective. So the objective for our experiment is to observe the relationship between the pressure and the temperature for saturated steam. And also the scopes for our experiment is the first one, the saturated steam uh, will be heated up to the temperature ranging from 97 degree to 100 degrees Celsius. So the maximum the better. Also we use zero point 0.5 bar increment and decrement for gauge pressure that will be set for the temperature reading to be taken. Also, the medium was used was the water.
Okay, thank you, Afina, for the explanation of introduction for experiment 1 Marcet Boiler. So now I'm going to talk about theory and working principle, but first let me introduce myself. My name is Fakhrul. Alright, so the Marcet Boiler experiment is primarily conducted to investigate the relationship between the pressure and the temperature in saturated steam, demonstrated how they are very in a closed system. And this relationship is essential for understanding thermodynamic properties and is the basis for steam table widely used in engineering applications. Okay, now when a liquid is heated in a closed system, it begins to vaporize, producing steam. In this state, when the steam reaches saturation, it exists in equilibrium with its liquid phase. For a closed pressurized system like Marcet boiler, the pressure of the steam increases with temperature. So the temperature pressure relationship follows saturation steam curve, which can be validated using experimental data and steam table. So right now we are still in the theory part where thermodynamic properties of a pure substance could be determined by two of the following characteristic: T, P, H, S, V, and etc. Data characteristic could be obtained either from experiments or equations or using certain. Among two thermodynamic properties that easily measured are T and P, so the relations between these properties could be expressed in the form of graph or equation. Clapeyron equation 1 has published the following. So we have VTDP saturated, TVG minus VF, HG minus HF, where we have the volume of water, we have Vg the volume of steam, we have the enthalpy of water, we have enthalpy of steam, and we have the heat domain of vaporization. Okay, so next, the experiment also includes the process of depressurization and pressurization. Depressurization is to remove the air pressure, whereas the pressurization is the application of pressure in a given situation or environment. Next, the working principle of the Marcet boiler. So, electricity heated boilers make use of the electric current running through a heating element to create heat to boil water into high temperature and high pressure steam.
My name is Mohamad Hanis and I will explain about the experimental setup and methodology. So first of all, this is the figure 5 uh, Marcet Boiler setup. As we can see, there is the figure with label. So I will explain one by one. So we look at one. Number one is drain valve. Two is heater. Number three is overflow plug. Four is filler plug. Five, safety valve. Six is temperature sensor. Seven is manometer. Eight, boiler with insulation jacket. Nine, temperature gauge. 10 is heater switch, and last is 11 is the master switch. Next, we move to the methodology part. First, open the filler plug and overflow valve. Step 2, fill the water into the boiler until the water flow out from the overflow valve. Next, we need to close the filler plug and tighten by using a spanner. And then turn on the main switch and heater. And then step 5, once the temperature reach 97 to 100 degrees Celsius, we close the overflow valve. And next is record the initial temperature at zero point 0.5 bar, and then the temperature rise is recorded for every zero point 0.5 bar increment in pressure until the pressure reach 5 bar. After we finish record the reading, we switch off the heater and then we record the temperature decrement for each pressure reduction of zero point 0.5 bar until final reading at zero point 0.5 bar in table 1. After all the reading of temperature is recorded, we can draw the graph pressure bar over temperature in degrees Celsius for heating and cooling process. Step 9, determine the slope of the graph. And lastly, the value of TVG over HFG is calculated by using table saturated water and steam. Then the value was compared to the slope that we obtained.
So this is our saturated water and steam table that can be obtained from our lab manual. This is the data that we obtained from our experiment. So as you can see, we changed the absolute pressure unit from bar to kilopascal, and also the temperature in degrees Celsius to Kelvin. So we change this value unit because we are going to use this value in our calculation part. This is the data that we plot into the graph, which is the temperature against the absolute pressure for increasing pressure and decreasing pressure. So we add the trend line and the equation of the line so that we can see what is happening here. So from the graph, we can see the behavior of the pressure and temperature. It shows that pressure and temperature are non-linear. So for the R square here, it's explain that the closer the value of the R square to 1, meaning that it matches the data trend. This is the graph of the mean temperature against the absolute pressure. As you can see, we add a two trend line, which is the linear and the logarithm. And also we included the equation for the linear trend line and the equation for the logarithm trend line. So from the graph we can see the behavior of the pressure and temperature is non-linear, and the R square value is represent the closer the value to the one, meaning that it's match the data trend. So in this experiment, we will use the equation of the this trend to compare with the theory, the Clapeyron equation, to see the behavior of the water in two phase, steam and liquid, and we will see the pattern of this experiment. Now we are going at the calculation part. So to calculate the measure slope, we will be using the equation of the logarithm trend line that we can be obtained from the previous graph. So the equation is y equals to 33.897 ln x minus 62.684. After that, we differentiate this equation to get dy over dx equals to 33.897 1 over x. So we substitute the value of x with the absolute pressure in kilopascal unit. So after that, we get the measure slope value. So next, to calculate the calculated slope, we will be using the Clapeyron equation, which is dt over dp equals to tvg minus vf divided by hf minus hg. So vg minus hf, vg minus vf and hf minus hg, we can obtain this value from the steam table. So for example, 396.39, which is the temperature in unit Kelvin, times 0.7496 divided by 2182, and we will be get 0.135. So to calculate the percentage error, the equation is measured slope minus calculated slope divided by measured slope times 100. So for example, is 0.13 minus 0.113 divided by 0.13 times 100, and we will get 13.26%.
For the discussion, we will discuss about the table 1, graph 1, and also the graph 2 that is been explained by Lukman before. So for the graph and the tabular findings, we will be using them for comparing pressure and the temperature, which both of them remain stable during this experiment. So for the graph one shows that the slope during increasing pressure, which is the M value, is 10.16, which is slightly steeper than during the decreasing pressure, which is 10.001, which this indicates that the temperature rises more rapidly with the increasing of the pressure compared to when it decreases when the pressure is lowered. So this proves that the slight difference in the slopes is because of the presence of a small hysteresis effect, where the system's behavior differs during the pre-pressurization and also the depressurization phases. So these two phases have slightly different uh, temperature increase and decrease. Okay, so the next one also from our graph of our experiment, we can see that the rate of heating is approximately identical for the heating process, but the cooling process needed longer time to lose heat compared to the heating process. Why this happens is because the hysteresis effect, which commonly observed in the thermodynamic process, happens, and this can be attributed to various factors. So one of the possible explanation is the time delay in the heat transfer. So during the pressurization, as the energy supplied to the system, so the temperature will increase more sharply compared to the depressurization. So however, during the depressurization, some of this energy is lost due to the factors such as the heat dissipation and also the friction. So meaning that when the depressurization, the heat losses occurs naturally compared to the pressurization where the energy is added into the system. So when the depressurization happens naturally, so this leading to a slower decreases in temperature. So energy losses such as those resulting from the inefficient insulation or mechanical resistance within the system also contribute to the naturally losses heat in the depressurization. So therefore, the difference in the temperature changes rates during the pressurization and the depressurization aligns with the expected behavior, which uh, which proves the thermodynamic theory. Next up is for discussing the graph 2, which it illustrates a positive correlation between the mean temperature and also the absolute pressure. That this graph shows how the temperature increases within when the rising of the pressure. So the two trend lines were applied into the data and also the graph, which are the first one a linear trend line and also a logarithmic trend line with the equation that is shown in the slide respectively. So the linear trend line suggests a constant temperature increase uh, where the temperature rises by approximately 0.1008 degrees Celsius for every 1 kPa increase in the pressure. So while the trend line shows a strong correlation of 97.90%, but the logarithmic trend line have stronger fit to the data with 99.55% variance. So this behavior aligns with the thermodynamic principles, which is as the pressure increases, the systems will absorb more energy, leading to a temperature rise. So, however, at higher temperature, the temperature increase will slows down as the system approaches to the equilibrium, which this reflecting the diminishing returns characteristics of the thermodynamic process itself. So the logarithmic trend line is more accurate representing this behavior as it accounts for non-linear relationship between the pressure and also the temperature. So initially it's more reliable and useful for calculation over a wider range, or simply said that we can actually use the logarithmic trend line if we are working in big industries to calculate in a very big wide range values. So from the table 1, we calculated the average percentage error. Then we got for our experiment is 25.58%, which is quite high because it is over 20% of percentage error. So based on this data, we can conclude that our experimental yield is not quite accurate, and this is mainly due to the several errors occurred during the experiment, which is the first one is the air in the boiler that is not fully removed, which can result in inaccurate experimental results since the partial pressure of the air can also affect the temperature within the Marcet boiler. Besides that, the wash valve is maybe not fully closed during the heating process, which can lead to a higher percentage error because the air inside the boiler will be measured as the pressure to the surface of the water. Other than that, the unwashed Marcet boiler can also contain impurities inside, where these impurities can messing up with the temperature and the pressure inside it. So it will cause the errors. Last but not least, which is the most low possibility is because of the parallax error that we might be done, that might also happen in our experiment while measuring the temperature and also the pressure. Next is how to overcome and minimize the errors. Is the first one, the Marcet boiler must be washed before using it to reduce the errors that caused by the impurities inside the boiler. Uh, After that, we can also avoid the parallax error by making sure that our eye level is perpendicular to the scale of the manometer. Since the manometer that is attached to the Marcet boiler is quite high, so we need to improve on how we are reading the scale of manometer, making sure that it is eye level. So next one is the wash valve must be closed to avoid the air inside the boiler from forming a pressure and being measured. So when the valve is opened, it actually takes a higher energy to change the phase of water to steam, and the saturated steam temperature can also be affected. Lastly, the air inside the boiler must be removed completely before conducting the experiment to avoid the boiler failure.
Okay, so what do we get from the experiment? So, in conclusion, the experiment achieved its objective where we successfully studied the relationship between the pressure and also the temperature for saturated steam. So, based on the graph that we have obtained from the experiment, the temperature and pressure are directly proportional to each other. So, the experimental slope dTdP obtained is compared to the theoretical value and determined through the calculation where when the pressure increases, the temperature also increases. The percentage error that we got from the experiment is 25.58%. It is due to the errors during the experiment. And we know that these errors need to be reduced in order to achieve more accurate results. For example, we can avoid parallax error by making sure the eye level is perpendicular to the scale of the manometer.